Welcome to day 2. We're just going to expand on projectile motion by combining two different projectile motion problems together to kind of see how they interact with each other, as well as try to figure out the minimum distance between two parametric equations. So let's get right to it. We have Caroline and Bea are standing 78 feet apart. At the same time, they each throw a ball towards each other. And then we have a whole bunch of information. So first thing we're going to do is just draw what this is going to look like. And I'm going to do that way up here just to kind of save myself some space. So I'm going to let Caroline be chilling over here and Bea be chilling over there doing what Beas do. And then just going to have Caroline throw it this way. Okay, but we don't really know how far it's going, and Bea's throwing it this way. Again, we don't really know how far it's going. So just a rough idea of what's going on. And what I'm going to do is allow Caroline to be at x equals 0, which means that Bea is at x equals 78. And that's really important for when we're setting up our equations. So I'm going to do that up here. Caroline, her equation's going to be x equals 45 cosine 44 t, and y equals negative 16 t squared plus 45 sine 44 t. They didn't tell us anything about initial height, so I'm just going to leave it as is. And then we have Bea's equations going to be, here's our first thing that's a little trickier. So since Bea starts at 78, I'm going to start at 78, and then she's throwing backwards in the x direction, so I'm going to subtract her equation here. So 41 cosine 39 times t. So 78 has her start way over there, the negative has it throwing in the negative x direction. Now her y value, we don't need to worry about that. Her y value is still going positive, so we can just leave that as it was with a positive 41 sine 39 t. And there are their two sets of equations. Next question asks, whose ball hits the ground first? So remember, when we're trying to figure out when things hit the ground, we're just setting y equal to 0, and then we just write what a, b, and c equal for each one of these. So negative 16, 45 sine 44, and 0. And then t is going to equal negative b plus or minus square root b squared minus 4ac all over 2a. And we're going to get 0 and 1.9537 seconds. And I'm going to store this one. And now what I'm going to do is not actually answer Bea's part first. Because I just stored that value, I'm going to continue right on and answer the next part because I already have these things stored in here. So let's see, that was part C. Part D is figuring out what is the horizontal distance that is traveled. So I'm just going to take that value that we just stored and plug it into the x equation. And when I do that, I will get 63.24 feet. And continuing on to the next part, part E, maximum height. I'm going to continue with this one because we know that t equals negative b over 2a when we're at the maximum, and we already have b and a stored in the calculator because that's the way our program works. So when I do that, I can literally write negative b over 2a, 0.976, that's the time, and then I just plug that value in to the y equation, and I get 15.268 feet. So I'm going to do all of that stuff for Caroline, and then I will basically repeat it now for Bea. So when does Bea's ball hit the ground? So I'm going to do y equals 0, a equals negative 16, b equals 41 sine 39, c equals 0. Doing all of that stuff again, t equals negative b plus or minus. And realistically, you don't need to rewrite this both times here. Just once is good enough, but you do need to rewrite what a, b, and c are. And I'll get t equals 0 and 1.612 seconds. And again, I'm going to store this. But at this point, we can answer the question, which is whose ball hit the ground first? And 1.6 less than 1.9, so Bea's ball hit the ground first. So Bea is the answer to this part. I'm kind of running out of room, so I'm just going to leave it that way. I'm going to take this stored value, and here's where things get a little bit tricky. Is this question does not ask for part D, where does Bea's ball land? So it doesn't ask where this x value is. What it asks is how far away from Bea did it land. So I'm doing a modified of this x equation. So I am doing x at 1.612 using that stored value, but I'm actually only going to plug it into this part of the equation. And that's just going to tell me what this distance is, so from Bea to where it landed. And I don't care about this 78 because I don't care about how far away from Caroline it landed, just how far away from Bea. So I'm doing 41 cosine 39 times the 1.612. And when I do that in the calculator, I'll get 51.38 feet. So we can see that Caroline's ball went farther than Bea's ball. For part E, same thing. Negative b over 2a. We already have a and b stored in the calculator, so I can just have this spit out the answer for me. So I got 0.806. I will plug in the y value at that time, and I get 10.4. So we can see that Caroline's ball went higher than Bea's ball. Now the last part of this, will the balls meet in air? So what we can see in the graph over there is that their paths certainly intersect. But remember, we have this third variable of time in here. So what we need to see is whether they actually intersect at the same time. So in order to do that, we're just going to do our standard collision formula, which is set the x values equal to each other, find the time, and compare the y's. So I have 45 cosine 44t equals 78 minus 41 cosine 39t. I'm going to just add this to the other side. So I'll have 45 cosine 44t plus 41 cosine 39t equals 78. Both of these have a t. I'll factor it out and divide everything away. So t is going to equal 78 divided by 45 cosine 44 plus 41 cosine 39. And when I plug that in that fancy calculator, I'm going to get 1.21 seconds. So what that tells me is that in this part right here, that this happens at some x value. We didn't actually figure out what it is, but the x values are equal here, and it's happening at t equals 1.21. So what we want to know is what is the y value at that time. So I'm going to do y of Caroline, 1.21, using the stored value, and I'm going to do y of Bea at 1.21. So when I plug both of those in, I get 14.36 and 7.73. So what that tells us is that at this x value, wherever this magical x value is when t equals 1.21, that Caroline's ball is up here at 14 feet, and that Bea's ball is right here, if I could draw, at 7.73 feet. Okay, so there's almost 7 feet of difference in between them, so they are definitely not meeting in midair. For example 2, we are being asked to find the minimum distance between two sets of parametric equations. And this isn't easy to do. If we take what we've already graphed from, a million years ago, it feels like now in here, if we were to go hit second calculate, you can see that there is no minimum value in here like there was back in function mode. So when we're in parametric mode, we can't quite do what we want to do. So we have a workaround. First thing we're going to do is switch ourselves back to function mode. So I'm going to go into mode and go back to function. That's going to give me my y equals like I'm used to. And what I'm going to carefully do is enter the x equation into the first line here. So I'm going to do 35 cosine 45, and then 45, come on computer, 45. And then I'm going to put x there. So everywhere there's a t, I'm going to replace it with x. Next line down, I'm going to do negative 16 x squared plus 35 sine 45, close parentheses, x plus 3. So that took care of this x and this y equation. In y3, I'm going to put this x equation, 50 minus 30 cosine 40, close parentheses t. And in y4, I will put this y equation, so negative 16 t squared plus 30 sine 40, close parentheses, t plus 3. Now, what we want is none of these to actually graph. So what I'm going to do is move the cursor over so I'm on the equal sign and just go and hit enter for each one, and you'll see that it makes them not highlighted anymore. And that's because I don't want it to actually graph any of those. And in y5, I'm going to put the distance formula in here. being very careful about how I line this up, I need to make sure that the two y equations are being subtracted and the two x equations are being subtracted. So my y's are both in 4 and 2, and the x's are in 3 and 1. So I'm going to do big old square root, parentheses. I'm going to go to vars, y vars function, and I want y4 minus vars, y vars function, y2, close parentheses, squared, plus, open parentheses, vars, y vars function, y3 minus vars, y vars function, y1, close parentheses, squared. Now, thing is that we're never going to have to do that again, because you're just going to leave this here for the rest of this unit, and all you'll have to do is modify the y1, 2, 3, and 4, just remembering that we have to go x, y, in terms of our parametric equations. So now if I go to graph this, I don't quite know how big it is. I'm just going to do zoom 6, and it's going to potentially take a really long time on your calculators because this is a complicated equation for it to do. Again, my calculator is being powered by a computer right now, so it makes things really easy for me. Since we are in function mode, when we go to second calculate, we have all of our normal things back. So I can go to minimum, and I can attempt to figure out where this is. So there's my cursor. I'm going to hit enter and go to the other side of it, hit enter one more time, and I got 1.03 for that x value, but remember that we entered in all x values were really time. So this is actually t equals 1.034, and the y equation in this case is actually the minimum distance. So these two parametric equations have a minimum distance of 5.68, which occurs at t equals 1.03.